Hello, everyone, and welcome to Link, Teledyne Ring's ongoing series of live and recorded webinars. We're very happy to be with you here today and happy that you can join us from around the globe. So today's webinar is going to introduce you to Teledyne Blueview's 3D scanning technology. It's going to be presented by John Robertson, who is our customer service manager. Before I get into the introduction of John, I do just want to launch a quick poll here, just so we can try and assess the experience level of the individuals that are on this meeting. It will just allow John to maybe shape his language a little bit to make sure that we are meeting you guys where you are. So you take a minute just to weigh in on one of those 3 easy answers. That would be fantastic. And while you are doing that, I would like to give a formal introduction for John. So John Robertson, as I mentioned, is our customer service manager for the Americas. He's worked with Teledyne Ring since 2008, starting with Teledyne Blueview. He was previously employed as an integration technician at Schilling Robotics. John has extensive experience with field operations using Blueview, Rayson, and Odin products. John manages a US-based support team that's responsible for all after-sales support for Blueview, Rayson, and Odin products, including training, field service, spare parts, product demonstrations, repairs, and coordination. So obviously, John is one of our busiest staff members based on that description. He certainly keeps busy both in the office and in the field. So John, just want to weigh in with the results here on this. It looks like the results are 44% novice beginners, 44% intermediate, and 13% advanced. So maybe that'll help you a little bit as you walk through your presentation. So without further ado, I'm going to hand this off to John.
Thank you, Margot, for the introduction. And again, thanks everybody for joining us today. So based on the poll, it's kind of a good beginning point for everybody to join this presentation here. Margot, can you hear me okay, just to verify?
I can, John. Yep, all good.
Okay, perfect. So without further ado, I will start with introduction on the product, and we'll go through some sample data and different ways of deploying the 3D sonar in different applications. So the product itself is a scanning sonar, which is what we call a profiling sonar that has a vertical field of view of 42 degrees and 1 degree beam width. The array, we call it, is built up of 256 beams that are 1 degree by 1 degree nominal beam width. The system has a max range of 30 meters and optimal range of 20 meters. The way the system works is the sonar is mounted on the pan and tilt, and we mechanically scan the sonar in 360 degree area to build up the point cloud as the sonar rotates around the area. And this is just a quick image example of the animated scene here, and the 3D point cloud data that you get out of the system after the scan is completed. We'll go into details on how that works moving forward. So the image display as the sonar is scanning around is displayed as a profile view. So you get a profile of the seabed, and in this example, the bridge footer here. And that comes across as the raw acoustic data display in the orange or copper data here. And then if you zoom in closer to the data itself, you can see the blue dots or lines that are placed on top of the acoustic data, which is telling you where the software is selecting to put points in the point cloud. So the based on the sonar or the software setting parameters, such as sound speed and intensity threshold settings, that's going to tell the software where to select points. There's a couple of ways to adjust that based on the environment you're working in. There may be some noise in the water column. For example, fast flowing water with bubbles in the water column or in a lot of environments, there's lots of fish. Those will be actually noise-causing items in the data. So there's a few ways to adjust that by adjusting the threshold intensity, or you can adjust the start range of the sonar so we can disregard data in the foreground to reduce the amount of noise that's collected in each individual scan. Just to quickly touch on the types of file formats that we get out of the system. When we record data, we record each individual scan in a file format called a .son file, and that basically records all the raw acoustic data from the sonar, and that gives us the capability to adjust things after the data is actually collected. So when you're in the field, you collect the data, and if you get back into the office and you see a lot of noise in the foreground, as I mentioned, you can replay this .son file in the collection software and reprocess it to generate new point clouds with a different threshold setting, sound velocity setting, or adjust those ranges, as I mentioned, to reduce the amount of noise that you're actually collecting. So that's just some ways that the software is flexible to be able to post-process. The only thing you can't adjust afterwards is really the position of the sonar. You want to make sure you collect the data in the area of interest to get the best quality data of the targets that you're looking to image. The TXT file is basically just a text file that includes any extra parameters that you input into the software at each individual scan, such as position information. Slight delay. Okay, here we go. So some basic deployment methods. We do have a standard tripod that is pictured here on the right-hand side. So this is a standard tripod that Teledyne manufactures. It has a swing arm here that allows you the arm to swing up to the top to give the center of gravity at the top of the sonar, and is easily deployed off of a surface vessel or a structure such as a dock or a pier, easily hand deployed off of the side there by one person. The tripod is adjustable to have to make the stance wider if there's maybe a little bit more current and need more stability, or to adjust it to make it taller. So this tripod can be adjusted to be about 6 feet tall up to about 9 feet tall, and that gives you some advantage of adjusting the position for the area of interest and the targets of interest. So some of our customers also like to deploy on the system on an ROV, and a lot of times we call that a flying tripod. In the basic form, the system doesn't need to be instrumented with positioning or heading information, motion sensors. So what that does mean is that during each individual scan, you do need to have the platform stable. So basically, from the tripod, we let that set down on the bottom, become stable. We conduct the scan. In the example of the ROV, we fly the ROV into the area of interest, and then we fly it down to the seabed, and then hold position on the seabed and conduct the scan from that fixed position. So a customized platform, we like to call this one low flat plate, or basically just a heavy steel plate, and you can see a little bucket handle here that swings up, and the center of gravity is up top. Both times that I've personally deployed this, we've used a small winch because it is a heavy plate. It's about 40, 50 pounds by itself. And if there is any current, we use it in a high current area, and it's basically a sail underwater. So definitely suggest using a winch to deploy this one. But the advantage of having the low flat plate is twofold. You're able to deploy in higher current areas to have a stable platform to get down to the bottom. It's difficult to have a light tripod deployed in current, because the water just takes it down, or the current just takes it down river or down current, and it makes it difficult to land straight up and down. With this low flat plate, it's much easier to do, and it gives you a lower perspective. You can see that the sonar itself is only maybe 18 inches off of the seabed. So if there's any areas where there's say a seawall or a bridge footer that has some scour or undercut around the bridge footer, you can get the sonar real low to the seabed and get the array to display or image into that undercut to get a really good volume calculation of the actual amount of material that's been removed from that structure. And we'll see a couple examples of that here in a little bit. So I mentioned in the basic form of the scanning sonar, you don't need any instrumentation such as positioning, heading, pitch and roll information. The system does need to be stable, but what that means is that each individual scan is not geopositioned in real world coordinates. It basically uses the sonar's pan and tilt axis as the 0, 0, 0, X, Y, and Z coordinates, and then that gives you basically a range and a bearing for where each individual point is collected. So when we have a larger area that we want to scan an image of, for example here, some pilings on a dock structure, when we do multiple scans, they're in their own coordinate systems. So we want to make sure that we have enough overlap in between the two scan locations so that we have enough common area, common seabed, and common structure to register those point clouds together successfully and accurately. You can imagine if there's not an accurate registration between these two scans, and then you add this one in, the third scan may have a little bit of error also if it's not good overlap, and then that just extrapolates the error from the first and the third scan. So it's very important to make sure you have enough overlap between them and common targets so that you can accurately register multiple point clouds together. So just to touch a little bit on the data acquisition flow. So ProScan is the data collection software that is used for the BV5000. This is the software we use in the basic form without any instrumentation. And you can see here the image display in the center. So this is the sonar's image display. Our range settings, so you have a start and a stop range to adjust your maximum range you're going to collect data at, and the start range to be able to eliminate any noise if there is any in the foreground. And then over here on the right hand side, you have your scan controls, your pan and tilt controls, and then a start scan button, which gives you another window to set your parameters for how fast you want to scan or what tilt angles to image at. Now, when we do instrument the BV5000 with a heading, pitch and roll, and positioning sensors, we can use multiple third-party software packages to collect data, but we call that capability motion scan because that does give you the capability to image from a moving vessel or a moving platform and scan at the same time. So we use the sonar's or the pan and tilt's feedback to correct for the geoposition from the GPS of where the points are being selected in the point cloud and displayed in the hydrographic software. So going back to the non-geopositioned coordinate system scans, so the individual ones from a tripod or non-positioned data sets, we kind of use this nomenclature: scan, stitch, deliver. So you're in the field, you scan, you collect the data, and then we get to the point where all the data has been collected and we need to register those point clouds together. We use third-party software packages. There's quite a few of them in the industry, but the basic features and capabilities are pretty uniform across most of them. So in this example, we have 3 scans that are of their own coordinate system, with the center being the 0, 0, 0, as I mentioned. And we manually drag and drop them on top of each other to be a best fit. And some of these point cloud registration softwares, you can use common features such as walls, not in this example, but pilings. There are in the seabed, so you use the common cloud face areas, and then we call that a cloud-to-cloud registration, and it'll do the registration, and then you get your final point cloud to deliver that to the customer. I know this image is a little bit blurry, but I'm going to go ahead and show a movie. This is a good example of some bridge footers that are in a river, and they're with the water flowing. You can see the green area here is the normal elevation of this riverbed, and the bridge footers are in the water column, and water flowing downriver is causing agitation in the water and picking up materials, agitating that material and flowing it downriver, exposing the under support structures of this bridge footer. So I'm going to pause it here for a second, and you can see the scan locations by these dark blank circles and throughout the data set here. And these are the individual scan locations that were taken and then registered to get together later. So the nice thing, as I mentioned before, about the perspective of this system, I believe this was collected with a tripod, or a lower, heavier tripod, and you can see the perspective is collecting data under this undercut, under the structure itself. So the good thing about that is you get the most accurate depiction or accurate volume and image measurements for this area. And you can imagine the municipality that monitors and inspects this would be happy to have this image, because they can go to contractors and say, here's exactly what it looks like under our bridge. Give us the most accurate estimate for repairing and remediating this structure. So the municipality knows exactly what kind of volume is in this area of material that's been removed, and so does the contractor. So they can give a more accurate bid on the project as well. This is a great example of post-construction verification. So similar situation to the previous bridge, but a different bridge. And this is an area that's had scour, and then had a contractor come in and do backfill, and then put in some protective remediation measures to prevent the scour from happening in the future. So the blue, so this is natural, the brown is the natural riverbed. The blue area is a concrete mud mattress, And this brown section here, that's the structure of the bridge itself. And then right around the structure is gravel bags. So the municipality that runs the bridge, maintains it, gave the contractor a specification. Here's what we want to do. And then the contractor came in with a bid and said, this is what we can do to fix your problem. And then the municipality, after they completed the project, used the 3D system to confirm that the contractor completed the project to specification. So it's an inspection tool from the beginning and then all the way to post construction verification. And again, you can see the telltale scan location donut holes here, we call them. This is an interesting one as well. So at a hydroelectric dam, this is a generic image here of trash racks, what are called trash racks, the intake of a hydroelectric dam or spillway, really any structure that flows water through it. But in the case of the example I'm going to show is a hydroelectric dam. And these trash racks are there to stop any large and major debris from going in the intake of the structure and going through the turbines. So in this case, I'll show the video. There was some debris and damage some debris that went through the turbine and damaged the turbine. So they shut down this whole section, this whole intake, and used the 3D sonar to deploy down through a manhole or an inspection hole inside the dam itself, and found that the trash rack had basically ripped off of the structure itself. And you can see I'll go back to zoom in a little bit. You can see the damaged pieces of concrete highlighted in red for display purposes along the sides. And then the trash rack that broke off and almost got sucked in itself into the intake. So again, there's kind of twofold here to inspect to see what happened and what the condition is of the area, and then also sending this data to whatever kind of repair contractors would be interested in placing a bid to do the repairs. They can know what it looks like down there and either make their plans on how they want to remove the material and repair from there. So touching base a little bit, moving forward on the motion scan portion, we have basically the motion scan portion provides you the capability to integrate the GPS heading sensors, mount the system onto a pole, and add a motion sensor onto the system. And then we have the sonar pan and tilt on the bottom. So similar to a multi-beam, traditional multi-beam echo sounder, but with a little bit different and limited performance as far as range and field of view capabilities. So this feature is we like to say is kind of an added tool to the capability of the BV5000 to give BV5000 owners more capability to this system. So I'll show a couple data examples of this in action. Okay, yeah, so the motion scan capability is primarily provided by the Teledyne PDS software package. It's basically a hydrographic survey data collection software package that has the added feature and added capability of taking in the pan and tilt feedback data, so that if you're in a fixed position or you are panning and tilting around with the BV5000, you can the software actually corrects for the pan and tilt changing where we're picking the points of the point cloud. So this is an example of what we would call, I guess, the traditional multi-beam mode. If you just point the sonar out into the side of the vessel and using the vessel's movement and not the pan and tilt's movement to collect data, gives you that added feature of collecting data this way as well. And this is a screen grab, a screen recording of the PDS software package. You have your aerial view on the left-hand side, and the right-hand side is your real-time 3D image display. So this integration was done with an INS as well. So when moving under the bridge itself, we lose GPS positioning, but then the INS takes over to correct for any GPS dropouts. And this is a nice example of an area that might be of interest for a municipality that's inspecting this bridge. When you can use the BV5000 in this mode, survey mode, to kind of get a broad overview, and then take the sonar pan and tilt off, put it on a tripod, and collect some more detailed imagery of areas of interest, which may be this pipeline or cable crossing the kind of junction point of when it goes up the bridge itself over here. So to fill in this area, they could drop the tripod, or even come over here, drive into this position, hold station, and scan this area to fill in this blank space as well, depending on if they can get the boat there or if it's not too shallow to get the boat over there as well. So yeah, okay, so this is some data examples of a pipeline inspection that was done in the same mode as the previous data video that we saw in the multi-beam mode. So we have a buried pipeline that was imaged without any with the motion scan capability, and then you can see this free spanning section of the pipeline on the end here. And the bottom image is a pipeline that was actually buoyant and suspended to the bottom of a lake. So this customer was interested to verify that there wasn't any tie downs broken, and they suggested that if there were tie downs broken, the pipeline would actually be floating or bulging up, not in a straight line, basically. So that was a good inspection, because there wasn't any damage in that area. This is a good example of a dam inspection, and we conducted in two modes, both in the traditional multi-beam mode with the BV5000 and motion scan mode, and in holding position scanning over on the right-hand side here. So I believe this lower image or lower scan was conducted from the vessel, just holding off on the side, but the data on the red platform, on the upper platform, that was done by a tripod. So shows the versatility of the system to be able to collect data in both modes, and with lots of flexibility. Okay. This is the same data example, but in a video form. So the municipality that manages this dam is actually interested in this section of transition from the concrete slab to the natural seabed. So they call that the sill. So the edge of that transition, we're very interested to see if there was any undercut or any large chunks that may have come loose, or rocks that may have come up onto the sill itself. So the managers of this dam can verify, if there's any damage that is or undercut that is happening, they can go in and remediate that damage before it causes further damage of the structure itself. Another case use for the scanning sonar is been using the system on an excavator or a dredging application, and typically a work site or a dredging site will be imaged by a multibeam, a 3D system that comes in and does a full area survey, and then establishes in the dredge software a DTM, a digital terrain map, and that is used by the operator to know where to dredge further and where not to dredge any further. So the use of the software gives the operators the capability to, as each individual excavation scoop, or each if it's maybe grappling hook, clamshell hooks, pulling out material, they can calculate the volume of material that is being pulled out, and adjust the DTM based on that. But adding a sonar into that mix gives the operator the capability to update the DTM with survey grade accuracy, so that they can successfully dredge the area and be 100% sure they're ready to move to the next location without leaving any material behind and having to go back to that area if after the survey or after the dredge project is complete. So they improve their efficiency overall by using a sonar, not having to go backwards. So this will be a video example of that, and you can see the outline. This is the DTM map I referred to. So you see the outline of the barge and the excavator structure here, and this white line depicts the sonar array, and it's going to pan across and update the DTM. So you have the gray, green, and yellow. That's telling the operator this area needs to be dredged. And then when it turns red, that means stop. You've dredged far enough. Don't go any further. So the video will show that basically at this point the excavator has removed some material, and then the next phase is to scan the area to update the DTM. So I'll show that video. So the area that we're going to be focusing on is here. You can see the real-time sonar display here, but the area to focus on is this area because that area is where some material has been removed already, and the sonar is going through and updating it based on the actual depth of the seabed or the area that they're dredging. You can see the color map change as the sonar panned by, and they went by twice because there may be some suspended material that could cause some noise in the area. So that's just one other case use, and I believe that is the end of end of the full presentation. Just a couple of data examples of projects that I've been involved in over the years. This is a really fun project that I was involved in. It was a steam-powered paddle wheel boat that sank in 1901 in the Yukon River in Canada, used in the gold rush era. That was almost perfectly preserved from the cold water of the lake on Lake LaBarge. And this data down here was actually in Osaka, Japan, and we used the BV5000 on a vessel to collect data using the motion scan capability. Okay, and let me see about questions. Okay, a couple questions I see. How far apart do tripod scans need to be to be collected? That's a good question. So the tripod scans without being instrumented, I believe is what you're referring to. Without being instrumented, it really depends on the environment. Because if there's lots of changes in the seabed elevation or lots of debris or not a lot of debris, that can change your spacing of the scans that you need. But in general, I would say about 10 meters apart so that you get a good overlap of structure and targets in between, and that gives you a good range of seabed coverage as well. But it also depends on your deployment method. If you're closer to the seabed, like the low flat plate or lower to the seabed ROV, then you'll get less seabed coverage that way. So you'll want to do closer scans at closer intervals. But in general, from a tripod, I would say about 10 meters apart is a good starting point. Next question I see is how long does it take to scan? So each individual location is different again, but you do have some parameters that you can adjust to increase or decrease the amount of scan time it's going to take. For example, if you look at the image here, this is a full 360-degree scan that we collected. So that would take longer than if you set the system to only do a 180-degree scan in the direction of the area of interest. So in this example, our area of interest is the structure of the shipwreck. So we could set the sonar to only scan the forward-facing 180 degrees, which would reduce the amount of time you would need to collect the data in that spot. You can also reduce the amount of time by increasing the scan speed. So we can you can scan from anywhere from 1 degree a second. Actually, I believe you can do a half a degree a second, and 1 degree, and then up to 10 degrees a second. So you can increase that speed depending on the data quality, density that you're requiring.
And John, I just want to note, I know we are at time, at the scheduled ending time. However, there's a lot of great questions. So John, if you've got the time and if people can hang out, I see a lot of just great questions coming through here. Just continue to plow through them, and whoever has the time, if you can stay on, that'd be great. Otherwise, we will be recording this session and have that available for you afterwards.
Yeah, sure. I'm happy to stay. I'm just trying to scroll through this a little better. I'm not seeing the.
Do you want me to read some off? I can just read some off if you like.
Yeah, that would be fantastic.
Okay, yeah, no problem. Okay, first one from Sebastian. Is there an existing driver for direct acquisition of Quincy, Q-I-N-S-Y? I should know that. Quincy.
Yeah, Quincy. Yeah, Quincy. For the BV5000, I don't believe they have picked up the pan and tilt portion of the data acquisition for the BV5000. I believe they have a driver for the multibeam side, the sonar side, but not the pan and tilts. That would definitely be a question we want to get answered by Quincy. We can definitely provide them with the, if we haven't already, with the software development kits to integrate both of those capabilities. But it's not out of the realm of reality to get done, but that is really up to Quincy to develop that capability. But I do believe we have worked with them in the past to provide them the information they need to do those drivers.
Okay, great. So Sebastian, maybe you could check in with Quincy, and if it's a thing that you're looking for, you could circle back with us on. So next question, in case of the WROV solution, is the input of roll, pitch, gyro plus position from INS DBL possible? Because acquisition in a world frame XYZ is always required. Question.
Very good question, and the answer is yes and no. So on a work class ROV, if you don't have the ability to land on the seabed to provide a stable platform, then to do individual scans, or if you're trying to do scans from middle of a water column of a structure, for example, an oil rig, you basically don't have the capability to hold station well enough to compensate for the motion. So yes, you can input those data points, position, heading, pitch and roll from almost any brand sensor into the PDS software, and do the motion scan from the ROV moving platform. So short answer is yes, from station keeping capability. It's just really integrating everything into the software package properly.
Okay, great, thanks. And now a question from Blaine. Hi, John. Is the BV3100 mount still available?
The BV3100, yes, that is still available. For everybody else, that's that product name is basically a pole mount with a pin and tilt on the bottom, and that typically is used for our 2D product line, and not usually used for the 3D. We don't have any standard mounts for any motion sensors on that pole, but it definitely could be adapted to hold a motion sensor on the pole to compensate for any wobble or anything like that. But yes, that product is available. And the other thing to consider with that, Blaine, is if on the top of that pole, there is not a standard mounting kit for a GPS. So you can use that pole as basically the mounting kit for the BV5000 on a surface vessel as a standard, but it would need some adapted parts to mount the motion sensor and the GPS antennas.
Okay, great. And a question from David. Can you give a statement regarding the accuracy of angle and distance?
Oh man, you're testing my my spec sheet knowledge here.
And if you don't have the answer, John, we can certainly provide that in writing afterwards. So or send the data sheet around. So.
Yeah, the angle accuracy is a difficult one to answer based on the detection algorithms. We do have a white paper that we have developed for offshore metrology, so very, very high resolution measurements from, specifically designed or specifically for open pipeline to open pipeline for designing a pipe to go between the two pipeline ends. So we do have a white paper that we can send you with very good information on those type of measurements.
Okay, that'd be great. David, I have your contact information, so I'll be happy to send that off to you. If anyone else would like a copy of that, just type it in as a question, say, send me the white paper, and I'll get that off to you as well here. Another one's from Sebastian. What about any silty material in the water column? Is the scanner able to scan through, or do we need clear water?
Very good question. I've only been in one working environment where the sediment load was too much to image through past about, I think I was only able to image about 8 meters. And it was during a high flow flood season. I believe it was a river in the United States. I can't remember the name of it, but it was very, very silty. I could put my hand. I don't know the parts per million. We don't have any laboratory testing of what we can and can't image through as far as parts per million goes. But this area, I could put my hand in the water and my hand would be covered in silt, basically. So yes, there is a limitation, but I can't tell you exactly what it is, but I've only encountered it once in my 12 years of using the system. So yeah, I apologize, I don't have an exact answer, but
No, that's okay. He said clear water, and that's definitely, we definitely can do it when it's not clear water.
yes, yeah, and probably 90% of the data that you saw on the presentation today was in low to zero visibility.
Okay, great. Another question from David. What are the processing software requirements for motion scan? And he has a second question, is the output still .son, .xyzi, or do you need another hydrographic software?
Our standard motion scan software is the Teledyne PDS software, and that collects the PDS files. You can also still record the .son files, but it won't include any of the positioning information. So ideally, you're just collecting data from the PDS, the hydrographic software package, and we can send you the specifications for. I believe you're asking for the computer specs to run that software package. We have a standard minimum specs and a suggested specs. Those software packages are very graphics heavy, so we usually suggest a high-end graphics card to operate those. So we can send you the computer specs if that is what you're asking for PDS. Please just get that and we'll send those out to you.
All right, great. And another question, this is from Parahan. Can we use 3D BP5000 for breakwater construction? Is it possible to monitor the placement of individual tetrapods during breakwater construction?
That's a very good question. So there's kind of a dual answer to that. So Teledyne PDS has a very specific package to monitor and deploy via positioning of tetrapods, and you can use the BV5000 in conjunction with that software package, not just as a virtual tool like the software would be. It's based on heading. You basically instrument the crane and the tetrapod, so you can get heading and positioning of the tetrapod for the software's needs, and then you can use the sonar that would be deployed strategically in the water to see where you're putting that physically. There might be a better solution or complementary solution to that. Also, maybe a 2D sonar to consider, because the 3D sonar it is basically giving you the point cloud after you collect the data or after you collect the scan. But that'd be something that we can discuss as a special application. But the short answer to finish my long answer is yes. It can be a supporting tool for that. Yes.
Okay, great. And another one from Sebastian. What's the relative angle of accuracy of the roll and pitch encoder measurement?
So if I am understanding the question correctly, so the sonar itself does not have a roll and pitch sensor on it. Any roll and pitch sensor that would be added for motion scan capability would be a separate device. And so with that said, there's a wide variety of motion sensors that can be used. Teledyne makes quite a few from the TSS brand. The data that you're seeing here with the tetrapods was specifically collected with the BV5000 on a pole, and the pole had a TSS DMS05 product. That's a motion sensor, pitch and roll, and heave sensor. And then the GPS position was collected with a hemisphere GPS antenna using RTK positioning. So it was very accurate positioning, which you can see this line in the data here. There's actually two data sets, the kind of a little bit brighter on the top, and then from here down is a little less bright. It was actually two separate lines that were collected, and they laid on top of each other without any correction. So that was collected with, as I mentioned, the DMS05, TSS DMS05. So yeah, the BV5000 by itself doesn't have any pitch and roll sensor internally. So I hope that answered your question.
Okay, great. And it looks like let's take one more here. I know we're knocking on 11 o'clock here Eastern time. So how long does it take to do a 360-degree scan at 0.5? Meters. I'm going to assume that's meters he's talking about, maybe distance.
Oh, at point, they said 0.5. So
yeah,
0.5 degrees. So it's a simple calculation. So 60 seconds. I think the answer is 12 minutes for half degree a second. So 360 degrees times 2 divided by 0.5. I believe that's the right calculation. That's seconds, and then divided by 60. 24 minutes. So that's half a degree a second for a full 360 degrees. And as I mentioned, you can increase that speed up to 10 degrees a second to be able to reduce the amount of time scanned. But then your data density and image resolution would decrease based on that scan speed, higher scan speeds.
Okay, that is awesome. Thank you so much for this, John. You guys, I'm going to pop up one more poll here because I actually am curious to see if people would be interested in learning more about this topic. I'm going to launch one more poll, so you can hang in there for just a couple more seconds. Fill this poll in for us before you log off. That would be really helpful and help guide us in the content that we're trying to create on our link page there and webinars. So apologies again for the technical difficulties. It's sort of the world we're living in these days. John, thanks for bouncing back from that one. It's always fun trying to make it come back after going through that.
Yeah, thanks for sticking around for the ending.
Yeah, absolutely. Yeah, well done, sir. So thanks, John, for all this. This is great information. If you have additional questions, please don't hesitate to reach out to me. I will not have the answers, but I will absolutely get you the answers that you're looking for, or, whether it's from John or one of the other amazingly intelligent people that we have in our organization. So please do reach out, stay engaged. John, thanks again. And we will have a recording of this that will get sent around. And thanks again, everyone, for your time. Have a fantastic day.
Take care. Bye-bye, everybody.